We will conclude the tour of the SMARTFIRE environment with an example case loaded from a DXF file. In this case, we will take the DXF file and we will import it into the Scenario Designer. We will use the Scenario Designer to interpret the lines and turn it into a scenario geometry. We will then export that as a SMARTFIRE model file, which will be loaded into the case specification environment, where we will continue to configure the case that we want to run and the scenario and to create the mesh. Once we have created the mesh, we will receive command script and a geometry file, which can be loaded and run in the SMARTFIRE CFD engine. We will then take the results and visualize them in the post-processing analysis program data view. So to begin, we start the case specification environment. I'm just going to change the background color to white to clarify the display, and then I import my chosen DXF file. It's vitally important as soon as you load a DXF file to check that the model units are correct, so that your scale interpretation is correct, and also to set the grid settings correctly. The grid settings are very important as they may determine the overall cell budget. This sets the accuracy with which you interpret the lines within the geometry. If you try to interpret the lines with very fine resolution, you may end up creating very small gaps as you interpret different surfaces with a small displacement between them, and in this case you can create a very poor quality mesh. So it's very important at this stage, at the beginning, to decide how refined you want your mesh to be when you get to the meshing stage. If it's a small geometry like this, you can probably get away with a fairly fine spacing of about 0.1, like 10 centimeters. But if you have a very large scale geometry, a whole building for example, you may need to go to 0.2 or 0.4 meters, or in extreme cases even larger. Remember, this is only setting the accuracy of the Snap2 grid in this tool. You can still have smaller cells than that in the meshing, and you can still edit the objects of real importance and change their positions if you need to. But it's a very good idea at this stage to set as coarse as you possibly can in the Scenario Designer, because this will really keep your mesh budget as low as possible, and with a reasonably high quality mesh as well. The first thing to do with a DXF file loaded is to check out the layers. We go to the DXF tab on the menu and select Layers. You can see the contents of all the layers that are available. When you select on them, they get displayed in pink. And in terms of using the automated tools within the Scenario Designer, we want to disable the doors. Therefore, human interpretation, they don't help the software to locate doors, so we can disable them. They then go to grey. We can also disable furniture, or in this case what we will choose later to be the fire, because we don't want these features to get in the way of our searching for the rooms. The walls we definitely want to keep, so we can just close the tool now. In order to start interpreting the geometry, we now need to create a story, and this is the outer boundary of the geometry that we're going to simulate. So we select, drag and select again to define the outer limits of the story, and at this stage it's worth checking the story height is correct, because that information usually doesn't come through the DXF file. In this case I'll accept the default of 2.6 meters high and the default ceiling depth of 0.2 meters. In order to use the automated room searching tool, you now select Tools from the menu and locate Rooms. The tool can find rooms based on double lines or single lines. And in this case we have double lines for the walls. So we select double lines and OK. And the tool has identified 3 compartments in this geometry. We can move all of those over to our selected or found rooms list and select OK. There is a problem because of the accuracy with which we searched the geometry, and that is that the room blocks are actually touching. The scenario designer works on the principle that room blocks which are touching are actually part of larger rooms with more complex shapes, for example an L-shaped room. In this case we have to make some decisions about how we will partition the space, and we can simply achieve this by dragging the edge of the room to the appropriate position. Again, you can see here that there is some interpretation needed, because that is one valid solution, that is another valid solution, and that is a third valid solution, based on the accuracy that I've prescribed for the Snap to grid. I will choose to move to there, and similarly on the bottom edge to there. We now have 3 room compartments which are completely separate. We can now select the other objects which define the domain. In this case we want to create some doors. And the doors can be positioned on either side of the gap between rooms, so either boundary of a room, and only one is needed because the software knows about punching through the wall in order to create the doorway. In the particular geometry that we have here, the only other additional object that we need to add is the fire, which we will place in the position of the furniture. Remember that this tool is only entering the geometry. There are no settings for the type of physics or the fire output or any other behavior, although we do have limited control over whether a door is initially open or closed. We can click on an object like a door, look at its properties, and we can choose its initial state to be open or closed. We can also at this stage choose the fire properties to choose the size of the volume of the fire. Once the geometry has been entered, it's then possible to select everything that you want to add to the scenario, and this will be the scenario that is taken forward for configuration in the case specification environment. I'll do that now by selecting Add Building to Scenario, and you see that the scenario window becomes populated with the geometry that we've just added. Geometry is now ready to pass on, so we can choose File, Create SmartFire Simulation, and enter a folder name for this working case. I'm going to choose CAD Import Demo as my meaningful name, and the tool automatically fires off the case specification environment with this geometry loaded in. I'm just going to change to using a white background, and remember that this tool, it's imperative to start thinking about the type of scenario that you're going to model in the CFD engine. So we go to Scenario and Problem Type, and we now set the physics activations that we need for the scenario that we're going to model. In this case, I'm going to activate the radiation model. I'm going to keep the combustion model deactivated. I'm not going to use toxicity or HCl, and I'm not going to use a sprinkler model, but I will have smoke active. It's worthwhile quickly looking at the configuration options for the modules that we've activated. The radiation is by default the 6-flux radiation model, although this can be changed. The smoke model has default values for smoke density, absorption constant for radiative interaction, and the smoke-specific extinction coefficient for optical considerations. These factors may need to be changed for the particular type of fuel or fire that you are burning or the conditions under which it's burning. You'll also need to consider at this stage the solution control, whether or not this is a steady state or transient simulation, and to set the time step size, sweeps per time step, and the overall simulation time that's needed. The convergence tolerance defines how refined the solution is at the end of a time step before it is allowed to move on to the next time step. The defaults are usually acceptable for the physical properties, but check that these are realistic for your particular simulation. Once you've activated the correct physics modules, it's then always worth going to the output control to check that everything that you need is actually saved. In this case, I'm going to deactivate saves of radiation. Whilst radiation will still be calculated, I'm not interested in visualizing it. Same goes for the kinetic energy and dissipation rate. I'm also not interested in the buoyancy or density, but I am interested in temperature, pressure, velocity components, and the smoke. The very important feature that I need to check is that the results are going to be saved and the frequency of those saves. And in this case, I want every time step to be saved, so I'm going to change the time between saves to be 2, which is the same size as the time step. If I have concerns about the stability of the simulation, it's also worth saving the restarts more regularly in case I find that things crash, go on numerically unstable, because I might need to control them and change them. In this case, actually being able to restart and change the control settings could be very beneficial. So once everything has been activated that you need activated and the frequency of saves is prescribed, you can then select these settings. We haven't yet configured the fire, so we can now select on the fire in the Object tab, and we can configure this fire to our needs. Remember in this case that the fire represents the flaming region as opposed to the item of furniture which is burning. So it may be appropriate to move this up slightly from the floor or to change its height to be more realistic flaming region if that is appropriate. In this case, I'm going to choose the height to be 1.2 meters. So whatever the item is that's burning and releasing gaseous fuel, I'm assuming that the fire will then be this flaming region up to 1.2 meters high. I also need to consider the properties of the fire, in which I open the fire properties window, and the first thing to consider is the heat release rate in kilowatts. I choose an expert fire, and I want this fire to ramp up to a megawatt. In 100 seconds. The smoke production is by default not activated, so there will be no smoke by default. There's a simple way that we can actually activate smoke, and that is to use an assumed heat of combustion of our fuel and an assumed yield for our smoke, and to calculate an equivalent smoke production curve from the heat release rate curve that we've already prescribed. In this case, I'll accept the 20 megajoules per kilogram heat of combustion and the 0.05 kilograms per kilogram smoke per fuel yield, and I will select calculate from HRR. This produces an equivalent smoke mass release rate curve. At this stage, the simulation is almost ready to run, apart from the fact that we haven't created a mesh. So we now need to choose Run and Create Mesh, and go through the same process of checking the geometry, checking for any issues. The meshing tool has worked out that there are overlaps in the geometry. In this case, it's okay to ignore those overlaps because they're the portals intersecting with the walls. And we now have the geometry type selection. In this case, it's a single floor of a building geometry. So I choose that option rather than the default and select OK. And the software now considers the extended regions that are required. There is one external vent on the high X surface, so this is not optional. We have to have an extended region on that surface. The other surfaces are all optional, and I'm going to choose to ignore those other surfaces and not create any more extended regions. So I simply select OK. And then we arrive at the cell budget for meshing. In this case, I'm going to choose the recommended refine option and select OK. And this is the base mesh that we arrive at. As always, it's worthwhile considering the nature of the mesh that's been created. In this case, it's still quite a coarse mesh. It's a coarse, fairly good quality mesh because all the cells are reasonably square and there are no very long thin cells. But actually it's quite a small cell budget and there are quite large cells. So in this case I'm going to perform a step refine in order to improve the mesh and add additional cells. If there's anything about the geometry that I see would require or may need more cells, then it's worth adding those cells manually using the manual edit mode to insert additional cells in regions where they would be most beneficial. This is particularly true in the Y direction and for any openings or apertures in the geometry. Once you're happy with the mesh that will be created, you can accept, and that will create a command script file and the geometry file for the CFD simulation, and then we can run the CFD engine from the Run CFD Engine tab.